Hello, I'm Seema and welcome to part 19 of the chapter Haloalkanes and Haloarenes. In the previous video, we were discussing the stereochemical aspects of nucleophilic substitution reactions, and I told you about optical activity and plane polarized light. In this video, I'm going to discuss the second aspect, that is we're going to talk about molecular asymmetry and chirality. Before I come to chirality, let us first take up molecular asymmetry. There's a very interesting fact. If you look at a ball is a sphere, and it's a very symmetrical structure. When we say symmetrical, if you go to the center of the ball, from the center, the distance from the surface to the center in all directions is equal. And the ball appears to be the same however you may hold it, it is still the same. Right? So it's a very symmetrical structure. And there's another very interesting fact. If you look into the mirror and you take a ball and you put a mirror in front of the ball and you look at the mirror, the ball as it looks here in my hand looks the same in the mirror. It has the same symmetry. It is absolutely symmetrical. Another very interesting thing that you could notice is that when you are standing in front of a mirror, just stand in front of the mirror, like I'm standing in front of the mirror, and in the mirror there is a person, a lady who's looking at me. That is me, of course, but someone who's looking at me. Now, if I raise my right hand like this, and I look at the mirror image, or I look at my own image in the mirror, that image raises its left hand in the same manner. I may be appearing to be raising my right hand, but the mirror image seems to be raising the left hand. It means that although to me, I have a feeling that this is how I look. What I'm looking at is not exactly how I am. What I'm looking at is a switched version of me. That is, my left is now right and the right is left. Of the image that I see, what I am seeing as left is actually my right. So whenever you look at your image in the mirror, that is not how the world sees you. The world sees you as you are. But what you see in the mirror is an image of you, which is actually the left is the right and the right is the left. And this is so interesting. And let us take a few more examples. Let us take this glass here. The glass is symmetrical. If I looked at a glass in the mirror, or in the mirror it appears, in my hand it is like this, but if you looked at it in the mirror, it would appear like this. That is, the left would be the right and the right would be left. I cannot actually show you the mirror image, so I'm turning it backwards. That of course is actually theoretically wrong that I'm showing you the back side, but yet considering that both the front and the back are the same, therefore I would be able to explain the concept. So if this is the glass as it appears, in the mirror the glass will appear like this. So can you tell which is the right side, which is the left side, or does the image in the mirror look different? No, it does not. So the glass is symmetrical. On the other hand, if I had this mug, the mug has a handle. And if this is the image of the mug and the handle is on the right, on my right hand. In the mirror, if I stand in front of a mirror holding this mug, in the image, the girl or the lady who is holding the mug would be holding it with her left hand. And this handle would be on the left. It would not be on the right. So this mug is asymmetrical. Just as I was, when I looked into the mirror, my right hand raised up was the left hand raised up. So this was asymmetrical. Similarly, a mug which does not have perfect symmetry would also be an asymmetrical object. A means not symmetrical. So it is asymmetrical, it is not symmetrical. So you've understood what symmetry and asymmetry is. Now, what is so important and why are we talking about it when we talk of the stereochemical aspects? There was a scientist whose name was Louis Pasteur. And Louis Pasteur in 1848, he observed this behavior in molecules. He observed that certain molecules are asymmetrical in their structure. And if they are, that means that those molecules would have differing mirror images. Their mirror images and the actual molecule would not be the same. And he found that these molecules are asymmetrical, and you could have both versions of the molecule. You would have one version of the molecule as if it is the molecule itself, and the other version of the molecule would be a mirror image of that original version. And he realized that these stereochemical properties like optical activity are there because of this difference. Because one of the molecules is whatever it is, the other one is a mirror image of that. So the left and the right are kind of interchanged between the two, and therefore they behave differently when plane polarized light is passed through their solutions. One of them would twist it towards the right and the other image would twist it towards the left. One of those molecules would twist it to the right would be dextrorotatory, the other would twist it to the left, which would be levorotatory, and the angle would be the same, because these two molecules are nothing but mirror images of each other. And this difference in the arrangement of their the atoms in the molecule is responsible for optical activity. So let us read exactly what did Louis Pasteur say. Louis Pasteur in 1848 observed that crystals of certain compounds exist as mirror images, and he laid the foundation of stereochemistry. Since they exist as mirror images, this fact becomes the foundation of stereochemistry. We see stereochemical properties or differences or stereochemical aspects because of the fact that these molecules are present as mirror images of each other. So this laid the foundation of stereochemistry. An aqueous solution of both of these, the mirror images, would in equal amount, that is of equal concentration, they would show an equal optical rotation in opposite directions. One would be dextrorotatory and the other would be levorotatory, and both would be dextro and levorotatory by the same angle of rotation. So equal optical rotation in opposite directions. And he believed that this property, why do they have optical activity? They have because they are mirror images, and they are mirror images because the arrangement of atoms is different in them. And it is this three-dimensional arrangement which is responsible for optical activity. So he believed that this depended on their three-dimensional 3D arrangements, and the 3D arrangements, which are also called configurations in the crystals. The 3D arrangements, the term used for 3D arrangements is configurations. So since they have different configurations, or since they have different three-dimensional arrangements, that is why they show optical activity. So stereochemistry in the case of nucleophilic substitution reactions is seen only in those molecules which are asymmetrical, which do not have symmetry. So since they are asymmetrical, they would be present as two forms, two mirror images of each other, and both the forms would then be isomeric, and they would show optical rotation. Optical rotation of plane polarized light, either dextrorotatory or levorotatory. One of them would be dextro, the other would be levo by the same angle. Then we come to Dutch scientist J. van Hoff and a French scientist C. Lebel. These, in the same year, that is 1874, they argued that the spatial arrangement of the four groups that are attached to a tetrahedral carbon. In most of the alkanes, carbon, the central carbon, we know carbon is tetravalent. It has 4 valencies. So if it is a saturated hydrocarbon, the carbon would have 4 different groups arranged to it. These 4, in the case of methane, for example, if you have methane, carbon is attached to hydrogen, 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 and hydrogen. If all 4 of these hydrogens, they are all 4 hydrogens. And what is the arrangement of the tetrahedral arrangement of methane, it is somewhat like this, right? Not exactly like this. Every angle should be 109.28 degrees. And if you hold the molecule like this, or you hold it like this, or you hold it like this, in every direction it is symmetrical. It has the same shape. One on top, three coming down. This comes on top, these three this way. This comes on top, those three. So it is a symmetrical arrangement. It is a symmetrical, not asymmetrical. It is symmetrical. But if these groups, instead of hydrogens on 4 ends, if you have different groups attached to the 4 ends, then the molecule becomes asymmetrical. Let us understand how. I took these 4 pens of 4 different colors, the 4 markers. The reason being that I wanted the different colors to be assumed to be different groups. Let us say that these are different groups. Now, I'm holding this molecule in the front of a mirror. Okay? Now, if I hold the black and the blue, if I hold them in the plane, in this plane, that is horizontally like this, then this pink pen is coming out, is coming forward, is going towards you. And the purple pen is coming towards me. Right? This is what is happening. The pink is going forward and the purple is coming back to me. If I look at the mirror image now, if I reverse, if I imagine that this is the mirror image and I reverse this direction. Now again, the blue pen and the black pen are in the plane, are in one plane, in the mirror. But now in that image inside the mirror, I see that the purple seems to be coming in front and the pink is going to the back. The pink is in that, now this is the mirror image. I'm standing here, pink seems to be coming towards me and purple going to the back. But if you really look at this plane again, pink is actually going back and purple is coming forward. So what has happened? The direction of the pink and the purple has been switched. So the molecule now is not the same as it was in this direction. When it was here, the pink was coming forward and the purple was going back. But when we took the mirror image, the purple was coming forward and the pink was going back. This itself, it is like me holding my right arm up and the mirror image holding the left arm up, which is asymmetrical, right? So this is what the scientists Hoff and C. Lebel, they said that in the same year they argued that the spatial arrangement of the 4 groups, that is the valencies, around a central carbon atom is tetrahedral. And if all the substituents attached to that carbon are different, if this was in the center, we had the carbon atom, and all the species which were attached to the carbon are different, then such a carbon is called an asymmetrical carbon. This carbon is not symmetrical anymore because every species is different and its mirror image would not be the same as the original molecule. So we'll say this carbon is the reason why the molecule is asymmetrical. Why? Because it is this carbon which is responsible for 4 different bonds around it. So it is the center which is causing asymmetry. Such a center which is causing the asymmetry and which is responsible for the stereochemical properties is known as the stereo center. So this carbon would be known as the stereo center. So he said that if all the substituents attached to the carbon are different, such a carbon is called an asymmetrical carbon, or it acts as a stereo center. So the resulting molecule, the molecule which will be as a result of this, where all the, let us say one is hydrogen, one is methyl group, one is ethyl group, one is propyl group, all groups are different, then they will have a different structure. So the resulting molecule would be asymmetrical, which would be responsible for optical activity. Therefore, this molecule would be optically active. And this carbon in the middle, which is the center of that asymmetry, it is known as the stereo center. Let us take some examples again of symmetrical objects and unsymmetrical objects. If you take a sphere like a ball, it is symmetrical, right? If you take a cube would be absolutely symmetrical. Or a cone, A cone would also, imagine this to be a cone, right? A cone would also appear to be symmetrical. If you look at it from this direction or you look at its mirror image, it will appear to be the same. A sphere, a cone, a cube, right? A cube, it's not the best example because one side is black and this is a cuboid. But if I hold it this way and we see the mirror image, imagining that this is not there, the black part is not there, then the mirror image will also appear the same. So this would be a better example because since all of it is black. So this is how it appears, and if we turn, it still appears the same, right? The image, the molecule has as it is, and its mirror image, both would appear the same. So it is symmetrical. So a cube, a sphere, or a cone would be symmetrical objects. And if you take an example of asymmetry, our body is asymmetrical. I told you the mirror image, if I raise one arm, the mirror image is not the same. If it is my right arm, it's the left arm for the mirror image. Therefore, asymmetrical object would be our own body. Take your hand. Your hand is also asymmetrical. See, when I say my right arm is the left arm of the mirror image, then my left arm should be the right arm of the mirror image. In other words, both our hands are actually mirror images of each other, right? Both our hands are actually mirror images of each other. And now there is a very important point that comes. Can you superimpose one hand over the other? Both of them are asymmetrical. Let me first talk about asymmetry. So a hand would be asymmetrical because it can be present as the right hand, it can be present as the left hand also, right? And feet, your feet are also non-superimposable. So objects, this mug is also asymmetrical. Your feet are asymmetrical. And what is non-superimposable? I wanted to explain that. Now take a look. This is your right hand and this is your left hand. If I want to superimpose them, superimpose means keeping one over the other, stacking them, putting one over the other. If I put my left hand over my right hand, can I put it over my right hand? What do I see? That they cannot be stacked. The thumbs are in the opposite directions. I can only join them and they can only be superimposed one exactly over the other if I rotate one hand. And if I rotate one hand and now I superimpose, thumb falls over thumb, first finger falls over first, the middle finger, the ring finger, and the small finger, right? These two images cannot be superimposed. They can only be superimposed when one is turned. And the moment you turn one, this has become the mirror image of itself. And only after turning it, you get the mirror image. So that mirror image is coming and superimposing on the other mirror image. So the superimposition is not possible if the molecule is asymmetrical, unless and until you rotate one of the images and then superimpose it. Right? Isn't this very interesting? So there is asymmetry, and asymmetrical objects, they cannot be superimposed on their mirror images directly. They can only be superimposed if you rotate one of the images and then place it over them. And this property of not being able to superimpose the objects that are asymmetrical, the two images that are asymmetrical, is known as chirality. And such molecules whose mirror images cannot be superimposed on them are known as chiral objects. And therefore, a molecule who cannot be superimposed on its mirror image would be known as a chiral molecule. And any substance which is symmetrical, if you have two of these, if I take this and its mirror image, which was like this, and I place them one over the other, you would not be able to tell. I can exactly superimpose one over the other. So they would be known as achiral. A means not, and chiral, it is not chiral. So we understand now what is molecular asymmetry. Molecular asymmetry is the lack of symmetry in certain molecules. It is present due to a stereochemical center, that is an atom around which all species that are attached are different, due to which its mirror image is not the same as the original molecule. The mirror image and the original molecule are different. They have different spatial arrangements, and therefore such a molecule is chiral in nature. And this is responsible, the chirality of molecules or the asymmetry of molecules is responsible for their stereochemical properties like optical activity, right? So now we'll go further and study more about chirality in the next video. Now that you've understood basically what asymmetry is, what chirality is, what optical activity is, and what is plain polarized light. So in the next video, we'll move ahead with our understanding of the stereochemical aspects of nucleophilic substitution reactions. So with this, I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.